Morning, everyone. So over the last 2 days, we've been looking at NMR. Essentially, we start off with an external field. We force protons to either align with the external field or against the field. We slowly cycle through our radio frequencies. If it's exactly the radio frequency that you need, it can cause the proton to actually flip from one orientation to the other. The first day we did was low resolution NMR. Basically, we ended up having just a single peak here. We didn't really have the resolution or the detail. Yesterday, we started looking at if hydrogens are actually on some adjacent atoms, depending on their fields, they can actually interact with the external magnetic field. They can make things slightly more stabilized or less stabilized here, causing some splitting in the pattern. So I just want to give you one example of that there. We're going to do a quick overview of something called X-ray crystallography, and then we're just going to put this all back together. What evidences can I get from mass spec, from IR, from NMR, to try to piece together what compound I've made? So this is a question from your textbook here. We have a proton NMR spectra of a compound. I've included the NMR data we're going to look at later on. So for this proton NMR, it has an empirical formula of C2H4O. It's shown below. They gave us the integrated trace, so previously it was hard to identify, well, how tall these are. It's a little bit hard to identify sort of the area under these peaks here. It's already been simplified, but at least these tell you the relative number of hydrogens. So these tell you how many H's in each environment. Okay, that's the first thing you can read. Second thing you can read here is how many peaks do I have? Well, I have 3 of them. That means I have 3 different hydrogen environments. I have hydrogens in 3 different kinds of places here. Remember, the shifting values here is going to depend on solvents and different conditions. They even tell you that on the data booklet. We always start off with 0 as our TMS peak. That one is slightly removed from the hydrogens that we care about, and we actually just measure how far downfield am I from this TMS peak. So first thing here says, see if you can determine the molecular formula of this compound here. You'll notice in total I actually have 8 H's, but my empirical formula only has 4. That tells you right away my molecular formula has to actually be twice of this, C4H8O2. Right, that's the only way for me to have 8 in total. So A was fairly simple. Draw some possible structures with this molecular formula. So let's think about index of hydrogen deficiency. If I had C4, I would have expected to be C10. In this case here, I have 1 degree of unsaturation. So that 1 degree here either means I have a double bond or I end up having a ring. Okay. And obviously I have some O's as well. Let's just try sketching some compounds. I only want to have 3 different environments. So let's just try here 1, 2, 3, 4 like that. Let's put an OH and OH. How many environments is that? Well, let's just plop down the rest of the hydrogens here. I don't know if this is the right compound, right? Well, first thing here, I have too many hydrogens. I don't even have the double bond. Maybe I want the double bond in the middle. I don't know. I'm just totally making it up here. Let's just count our environments. So we have the hydrogens bonded off the oxygen group here. That's one environment. I have hydrogens, the CH2s here bonded off oxygen. Those 2 are in the same environment. These 2 are in the same environment. This is a possibility. That's the sort of right number of things. I could also be, let's say, maybe even a carboxylic acid. So 4 like that, and then I have an O and an H like this. Let's count how many environments do we have. So we have 1 environment. I have 2nd environment, 3rd environment. Although both of those are CH2, the one that's closer to the electronegative groups here, this one here would be expected to be shifted further downfield. It's going to be even farther away from TMS. This one here, nope, this one actually has 4 environments, so may not be this one here. All right, so let's see if we've got it here. Do I have this 2 to 3 to 3 ratio if I have this orientation here? Well, I have a 2 to 2 to 2 ratio. Okay, so that doesn't actually match up. So far, right, we're still sort of scratching our head here. We don't really know what has happened here. Maybe we actually have a ring. Maybe we have 4 carbons like this, and we actually have an OH and OH. Remember, the ring itself would be 1 degree of unsaturation, and therefore, so I have one environment, that's one single environment here. I have an H on the ends of these, that's another environment, and I have the CH2s. Those are in a 3rd environment. That's possible, but again, same problem, 2 to 2 to 2. So far, based on what we know previous, it's hard, right? We need some more hints. So what they're actually asking you here is, okay, let's go to our data booklet. Let's see if actually looking at the shifting value, I know it gives you a nice range, but see if that actually hints to what's happening. So I have a value here, maybe 1.3, 1.4 or so. That one there, possibly I have a CH2 and an R group, right? It could even be a CH and R2 group. Those ones there are in that vicinity. I have one around the 2 point something, so maybe I have a carbonyl group, and it's actually these hydrogens here. Maybe I have a carbonyl or a carboxyl functionality. And I have one at 4.1, 4.2, maybe I even have halogen. Well, no, I don't have a halogen there. 3.3, 4, maybe I have this sort of functionality. Maybe we're actually an ester. So that actually gives me a hint. Okay, so let's try it out. What if I have 4 carbons? I have an ester of some sort, right? That ester needs to have a C group on this side. I need to have 4 carbons in total. It's possible here that it was just a carbonyl beside carbons, so that tells me maybe I have CH2s there as well. And then I have a CH2 with an R group, so probably that means I need to have another carbon group. So let's see if this one ends up working out. So first thing here is it's nicer because it does have the ratios that we expected to see, a 2 to 3 to 3 orientation. That's what gave me there. We already mashed up the groups here. We can even identify which peak is which. Let's use what we know about splitting to actually figure out what happens. So this CH3 here, there are no hydrogens on the neighbor. So we're actually going to have a 3 hydrogen singlet. We're going to have something that's 3 hydrogens tall. Maybe that's this one here. This one here is probably my methyl group on the end there, bonded to this side of the ester. I have a CH2 group here that's sort of mid-chain. My neighbor has 3 hydrogens. I'm going to now be 2 hydrogens tall. Right? That's my area under the peak. That's my integrated trace. But I'm going to be split into a quartet. Which one is split into a quartet? Well, maybe these ones here. 2 hydrogen quartet. That seems to match. So that would be this one. So that would be the CH2 sort of in the middle here. And I have one more just to make sure it's consistent here. I have another CH3. On my neighbor, I have 2 hydrogens. I was already going to be 3 hydrogens tall. I already worked out the ratio 3 to 2 to 3 like that. And this one here, because I have 2 H's on the neighbor, that's actually going to split me into a triplet. So 3 hydrogens triplet is probably this one here. So that would be at least consistent with it. At first, we were able to draw so many different molecules here. It wasn't really helping. By actually looking at where the shift actually occurs, it actually gave me a little more information. Probably this is the structure that we have. All right. We're going to quickly switch over here, take a look at X-ray crystallography. They say for this section, you don't actually need to know how X-ray crystallography works. What you need to know is X-ray crystallography is used to identify bond lengths and is used to identify bond angles. Okay, usually multiple choice. Which of these techniques can be used for those two? That's what you find. That's all you need. But just to give you a feel of how this ends up working, I'm just going to give you a little bit of detail. What we're going to do is we're going to send in X-rays. That's why it's known as X-ray crystallography. What we're essentially doing is we're sending really high energy X-rays. We're sending it into the structure. And what we're doing is we're watching sort of the shadowy pattern, what's left behind, as the X-rays actually interact with this crystalline structure. The crystalline structure, I would imagine, it's a nice ordered lattice. Let's just imagine here, it actually hits this lattice here, sort of at an angle here. First thing is the X-rays, we send it in as monochromatic. We don't send in sort of many different energies of X-rays. We just send in one uniform set of X-rays here. And we also send it, what's called in physics here, we send it in phase. We send it in so that when one of these X-rays here is hitting a crest, the other X-ray is also hitting a crest here. Okay, so everything is in phase, everything is constructively interfering. What's going to happen here is we're going to send these X-rays here, they're going to interact with the electron in the substance, and they're going to cause a different diffraction pattern. That's going to be a different sort of shadow. So what's ending up happening here is, let's imagine my X-rays are hitting this first layer. Depending on which layer that actually reflects off, my X-rays may actually end up traveling different distances. At first, they came in sort of in phase here. This first wave here maybe only got to this center part here, and it actually already bounced off, right? The other X-ray may be a little bit more lucky. It came in phase. You'll notice this one here ends up traveling a little bit more distance before it ends up reflecting off. So what I want to show you here is, because the X-rays have actually traveled a little bit more distance, depending on how many how this relates to wavelength, when these X-rays here end up leaving, I have a couple possibilities that can happen. If this extra distance, if the extra distance is no doubt that this blue X-ray here is traveling farther, if the extra distance is some multiple of a wavelength, maybe one wavelength or another wavelength, by the time they match up again, they're going to be perfectly in phase. When they leave and they're perfectly in phase, this is going to be constructively interfering. It's actually going to give me a bright spot on the diagram. What if the extra distance is exactly 1/2 of a wavelength? So let's do it here. They came in perfectly sort of in phase. This one here sort of left. And the other one here, based on the extra distance that it traveled, by the time it actually is leaving, this wave is actually going through a trough, crest, like this. It's perfectly out of phase. And in that case, when one wave is trying to be a maximum and the other wave is be a minimum, it actually gives me a destructive interference. Destructive interference ends up giving me no spot. Right? And we end up getting a sort of gradient here, depending on how much extra distance that actually cuts through the crystal, depending on how this relates to the size of a wavelength. That's actually going to give me a really bright spot, and then destructive interference, no spot, and then another bright spot here. It's going to give me a shadowy pattern based on how much extra distance was actually encountered. So what this ends up doing is it ends up giving us, really it's just a shadowy pattern. We call it an electron density map here. They took the molecule here, anthracene. It's the first molecule that we're seeing actually has having fused rings. Like benzene, they had that electron delocalization. They've done this X-ray crystallography to a sample of anthracene, and this is the shadowy pattern that was left behind by the anthracene sample. So here's your sample. We sent in our X-rays. We sent them all in phase. We sent them all in sort of when one's a max, the other's a max. As they interfere with each other, the bright lines themselves are still constructive interference. Whenever one was a bright line and the other one was a dark line, we end up getting a no line. And therefore, you end up seeing, this is the shadow. This is the diffraction pattern. That's the name for it. This is what's left behind after the X-rays have actually interacted with the anthracene molecule. And why did I say early on, how come this can measure bond length and bond angle? Well, we know anthracene is going to be sort of carbon rings here. Well, how far is carbon from carbon? There's the bond length, what's the bond angle? Based on this shadow here, we can actually identify what the bond, like how long and the angles between them. In fact, maybe 50, 60 years ago when they discovered DNA structure, this is exactly what they did. They had a sample here of DNA. They didn't know what it looked like to begin with. They sent in these X-rays, and they end up getting a shadowy pattern, and they could actually infer, oh, my DNA actually has to have a double helical structure. It's like a ladder structure here that sort of winds on itself here, so that as the X-rays here were passing through, as they interfered sometimes constructively, sometimes destructively here, so that it can actually give rise to this diffraction pattern. So looking at the shadow, we can infer what the sample actually looks like. Again, you don't need to know that technique in detail. You just need to know X-ray crystallography is one way that they do to actually determine bond length as well as bond angle. Okay. So let me just give you a quick summary over some of these spectroscopic techniques, and then we're going to do one combined question, definitely more practice questions for you under the resources section. So far, we have a few different hints here. We have an index of hydrogen deficiency. Basically, I lose 2 H's per ring or per multiple bond. Usually they call that a double bond equivalent, right? So I would expect starting from C and 2N plus 2 for the hydrogens. Depending on how many degrees of unsaturation, that tells me how many multiple bonds or whether I have multiple bonds present. Second one here was using mass spectrometry. This one here was using a electron bombardment, ionizing it, breaking up into fragments here. We would end up getting a mass fragment. The number of hits here, the highest peak here is going to be the molar mass of the parent. So parent ion peak. What was important for this one was our table would actually give you a bunch of values. Let's say the 15 that I always come back to. It's only positive charges that are actually deflected through the mass spec. So if you're not positive, it won't show up. We can look for the number as is, or we can look for, if I had my parent that had this molar mass, if I lost something with 15, what's my leftover peak, right? So those are two ways of looking at a mass spec. Using an IR radiation here, remember we send in a baseline, we plot a percent transmittance. We're fully expecting all this IR radiation I send in to fully get through, but based on a particular wave number was a way to measure energy in units of centimeters minus 1. If it was exactly the right amount of energy, we actually had particular bonds here actually absorb. Maybe I have a C11O absorb at a particular wave number here. Obviously, you can find, oh, here's the wave number. What bond do I have? The other thing you can look for is what's not present. So we saw for hydrogen bonding here, there should be a broadening here. So broad peak for hydrogen bonding. If it's not present, we can also identify, okay, well, probably I don't have hydrogen bonding. For IR radiation, the important phrase is you have to have a change in dipole moment. Not necessarily you need to be polar overall. We saw CO2 was actually nonpolar. The dipoles canceled. But depending on how it ended up stretching, it ended up overall being IR active for some modes. Then for NMR, the one that we just ended off with here, NMR, both low res and high res, essentially we start off having 0. This was our reference peak, our TMS, slightly removed. We're going to have, depending on how far shifted I am, a certain number of peaks here. The number of peaks, so in this case here I have 2 peaks. Number of peaks tells you the number of H environments, how many kinds of H's that I have. The height of the peak, or what's realistically the area under the peak here, the integrated trace, tells you how many hydrogens in each environment. And then what we did was for the splitting, peaks are split via Pascal's ratios, Pascal's triangle, according to n plus 1, where n is the H's on an adjacent atom. Okay. Depending on how that one, it can either help the external magnetic field or harm the external magnetic field here, causing a little bit of splitting upwards of quartet, or you just say complex splitting pattern. So now all these techniques here work together in this last problem that we're going to work through. We have an unknown compound. It's found to have a percent composition 85.6, 14.4. They're first asking us empirical formula, right? That gives me some information. Let me just copy this down here. So carbon is 85.6, so that means hydrogen is a 14.4, right? So empirical formula you did way back in chapter 1. Let's assume we have a 100-gram sample. Why do we like 100 is because these percentages would naturally be grams. The first thing I need to deal with is actually their molar mass. So 85.6 divided by 12. Keep extra decimal places. Eventually we're going to round to 1 decimal anyways. 7.1333 repeated. 14.4 divided by 1.01. I guess I should do that in a little more precisely here. Sorry, 7.127. 14.4 divided by 1.01 gives me 14.257. These are now actually moles. These are now ratios. I can actually compare them. I now need to just find the ratio between these two. So let's divide out the smallest one. Let's divide out 7.127. That should pretty much give me 1 to 2 as a ratio. Perfect. So my empirical formula is CH2. This has been a simplified ratio. For every 1 carbon, I should have 2 hydrogens. Let's see what's the next information. They gave me a mass spectrum next. This is shown below for this compound. Let's find the molecular formula. Well, the molecular formula would be some multiple of the empirical unit here. I notice that the heavy mass here, I'm going to assume that this is my parent. If my parent weighs 84, my empirical formula here, this would be about 12, this one here would be about 2. My empirical formula weighs 14. If I was supposed to weigh 84, how many 14 units would I need to weigh 84? 84 divided by 14 means I have 6 units. So therefore, I already know my molecular formula would have to be C6H12, 1 to 2 ratio. Now that I have my molecular formula, let's talk index of hydrogen deficiency. This one should have been C6H14. I noticed from the saturated compound, I would have actually lost 2 hydrogens. So that actually gives me an index of hydrogen deficiency at 1 degree of unsaturation. That either means I either have a ring or I have a double bond. Right? Those are the only 2 possibilities. Now, having a double bond, it could be an alkene, it could be C11C, or it could be just C11O. Okay, so let's just keep going here. Well, what are some possibilities? You'll need your data booklet to actually look up some of these values. Let's look for these numbers directly. So the 28 group here, on table 28 here, the 28 group here could very well be an alkene. So it could be a CH2, CH2, or it could be a C11O. Well, that's not helpful. It just tells me there's a double bond. These ones here would have to be positive for it to actually be sensed here. I don't have anything shown at 42. I don't have anything shown at 56. Remember, I can also do the difference. Starting from my parent of 84, how much would I have to have lost to end up being 56? 84 minus 56 gives you, I had to drop by 28. Oh, great. If I end up losing a carbonyl group, this is what's left over of the molecule. It's the whole compound, but minus maybe the carbonyl group or maybe the alkene group, right? So that's a possibility as well. How about 84 down to 42? 84 minus 42, oh, it's 42. So if the thing was exactly cut in half, that could be this bond. At the moment, I don't know what it is. But I do know the index of hydrogen deficiency is 1. Either I have a double bond or I have a ring. Is this molecule likely containing a CH3 group? Well, a CH3 group here would have a fragment of 15. If this one here were a positive, I don't have a peak at 15. So since it's not there, I would say no, because there's no mass peak at 15. Okay. The infrared spectra shows that there's one absorption that's close to 2900. The other one, there's no absorption at 1600. So let's look at table, let me cite these for you here. The mass spec table here is table 28. Let's flip over to table 26 here. It tells me you do have something at 2900. The only one at 2900 here, we have one quoted 2850 to 3090. Could be that one. It could be 2500, 3000. This one here at 2900, I think they're hinting at we have a CH bond. Well, that really doesn't help, right? Most organic compounds have C and H. But probably more importantly, there is no absorption at 1600. Well, what's close to 1600 here? 1600, it could, maybe the closest one that I have here is between 1620 to 1680. That would be a C double bond C. Because I don't have something there, it probably tells you you don't have an alkene. So while on the mass spec we were saying, well, it could have been CH2, CH2, that sort of chooses maybe I actually have more so a carbonyl functionality. So that's what I can deduce there. Deduce the molecular structure from the NMR. Why is there a peak at 0? Well, this is just my TMS. This is my reference signal. Oh, this one here only has one peak. So I only have one hydrogen environment. I only have a hydrogen show up in one way. But you notice it's a very, very strong environment. It means I actually have a lot of hydrogens in this environment. So what molecule here would be consistent with this? If I were to draw any molecule, I have right now here C6H12, right? If I were to draw any molecule, we have, let's say we have 6 carbons in a row, right? And I have hydrogens. I would at least already have 2 hydrogen environments. Some are a methyl group, some are just CH2, so that's probably not happening here. So the only choice I have here, especially if I have a double bond, I even get even more environments. The only choice that I really have here is maybe I have a cyclohexane ring, and therefore I have all 12 H's in the same environment, and therefore probably this structure here. Okay, so you see, you just sort of try to do it by deduction here, see if you can figure out what you have present, and therefore I have some evidence for this being cyclohexane. You can go back and you can just verify here. Well, earlier I was saying possibly a C11O. Maybe that's the functionality that we had, but C11O would need to have a actually an absorption. C11O would absorb 1700 to 1750. That's C11O. By them telling you that there's actually no absorption for 1600, they're even telling you that there's no C11O as well, which is between your index of hydrogen deficiency. I could have had a multiple bond, I could have had a ring. Well, the multiple bond that I had, well, I don't have an O. That's one problem as well. But because I don't have a peak on the IR spectra, that sort of gives me evidence again that it's a ring. Okay? So you see how these ones here can be actually put in detail together, all giving us hints to our molecule. Okay, keep practicing through some questions and just let me know if you have any problems. Thanks, guys.